So we've refreshed your memory about the properties of acids and bases, but how can we explain those properties? Acids have similar properties, so they must have something in common. They must all do something in a solution that gives them those properties. Bases have similar properties. They must do something. They must have something in common, which causes them to have similar properties. In introductory chemistry, you learned about the Arrhenius theory of acids and bases. And Arrhenius' idea was that if you have an acid, it must be giving hydrogen ions to a solution. So one example of an acid is hydrochloric acid, HCl, aqueous HCl. And what Arrhenius said is if you take this HCl and we're going to put it into a beaker of water, what's going to happen to that HCl? Well, when you add it to the beaker of water, it's going to ionize. It's going to come apart into ions. And the ions that you would get would be H plus ions, and you would get Cl minus ions. And he recognized that acids tended to be things that had an H plus and that were high solubility, so they would dissociate and give an H plus in solution. So he said, okay, well, maybe that's what acids are. Acids are things that dissociate into H plus and Cl minus. And for bases, Arrhenius noticed that bases tended to be things that had a hydroxide ion in them. And when you added something with a hydroxide ion, like this sodium hydroxide, to solution, it would dissociate. It would come apart into its ions. So the sodium ion would separate from the hydroxide ion. The O and the H stay together because they're a polyatomic ion, right? But they would be separate. And he said, when I'm looking at bases, I see this OH minus. I see this hydroxide ion coming up all the time. So maybe that's what bases are. Bases are things that dissociate to give the hydroxide ion in solution. But there were a couple of problems with this. Let's start with the acids. The problem that Arrhenius had with the acids was this hydrogen ion, this H+. So that thing is so friggin' small. All it is a single proton. It doesn't have any neutrons, doesn't have any electrons. It is one teeny tiny proton floating around. And it has a charge of 1+. That means that the amount of charge it has relative to the amount of mass it has is really high. It has a very, very high charge to mass ratio. And that would make this hydrogen ion incredibly reactive. It's going to want to react with anything that it's going to come across. And right now, where is it sitting? Well, it's sitting in a beaker of water. And that means that it's surrounded by all of these water molecules. And so we theorized that the hydrogen ion by itself, it probably isn't really going to exist. You add this H plus to the solution, it's going to want to react with the first thing that it sees because it has such a high charge to mass ratio. It's sitting in a beaker of water, so what's the first thing that it's going to see? Well, it's probably going to be a water molecule. So as it runs into this water molecule, what it will do is it will bond to the water molecule and it will make this kind of weird water molecule that isn't water anymore because it's got an extra hydrogen on it. This thing here now is called hydronium. This is a hydronium ion. And a hydronium ion then is what we theorize actually exists when an acid is added to water. So let's go back to my acid, my HCl. In the modified Arrhenius definition of an acid, when we add this HCl to water, instead of just ionizing and forming H+, it's going to react with the water molecule. The hydrogen is going to be transferred over to the water molecule, which is going to form hydronium. And chloride will still be left behind as an anion floating in the water. So what's actually happening in my reaction here? I've got my hydrogen chloride. It reacts with my water molecule. And when it does so, it transfers this hydrogen over to the water molecule, which is going to give me this funny water molecule that's got an extra hydrogen. And that we now know is called a hydronium ion, which has got a positive charge. Right? That's the water with this hydrogen. Then who's left over? Well, this chloride is left over. It's all on its own as Cl-. So this would be showing us then the modified Arrhenius explanation for why hydrogen chloride is an acid, because it can react with water to produce hydronium. Now, what about on the bases side? Turns out Arrhenius' original definition of what makes a base also needed to be modified, but not for the same reason and not in as many situations. Turns out Arrhenius' original definition for what makes a base, something that can dissociate to give hydroxide ions in water, that was pretty good. And that works for any bases that contain hydroxide as part of their chemical formula. And strong bases all contain hydroxide as part of their chemical formula, sodium hydroxide being one of them, potassium hydroxide or lithium hydroxide. Those would all be strong bases as well because they contain hydroxide as part of their chemical formula, and they would all have basic properties. Now, what though about bases that don't? And it turns out that there are bases that don't have hydroxide in them at all. One example is ammonia. Ammonia is a base. It's got a pH greater than 7. It would turn litmus blue. It would feel slippery to the touch. It would have basic properties. But there's no hydroxide in ammonia. There's not even an oxygen in ammonia. So how is it that it can act as a base? And the modified Arrhenius hypothesizes that something to be a base, it doesn't have to contain hydroxide within it as long as it can react to produce hydroxide. So what we would theorize would happen when we add this ammonia to water is it would react with the water molecules that are floating around. And it doesn't want to give water one of its hydrogens, but it wants to take one. So it would take one of water's hydrogens, and in doing so, it would form the ammonium ion, NH4+, which you have seen before as a really common polyatomic. Well, it's a commonly used because it's one of the more common positively charged polyatomic ions. And then hydroxide would be formed as well as a product. And so even though the original ammonia didn't contain hydroxide within its formula, because it can react with the water to form hydroxide, then ammonia can be explained as to why it's acting as a base. So the modified Arrhenius theory says something is a base if, like this ammonia, it can react with water. And when it reacts with water, it will not give a hydrogen to the water, but it will take one, right? It's going to take one of these hydrogens away from the water. And in doing so, then, we're going to make, in this case, ammonium NH4+, 1, 2, 3, 4. And my byproduct, which is the one that we really care about, is the hydroxide ion. And so this is the part that makes the base a base. The modified Arrhenius definition, a base is something which can react with water to produce hydroxide.